Welcome viewers to the second part of Compton Effect. In this video you will learn how Compton applied Einstein photon and relativity theories to theoretically explain the existence of longer wavelength in his experiment. To get familiar with the experiment of Compton, do watch the first part of my introductory video on Compton Effect. To provide a theoretical background to the experimentally observed behavior of the phenomena, Compton proposed a model in contradiction to electromagnetic theory and in agreement with Einstein's quantization theory of radiation. In short, he considered the incident radiation consists of photons, that is Einstein's photon theory, interacting with an electron of the target atom. He treated the model as an elastic collision between two particles, that is photon and electron, with few more plausible assumptions. That is, he assumed that the collision can be treated as a problem of relativistic mechanics. Why? Because it involves the scattering of photons that are massless and move with the speed of light. And the energy transferred to the electron is comparable to the rest mass energy. Number 2. Consequently, the energy and momentum of the photons and electron must be expressed using their relativistic values. Number 3. The laws of conservation of energy and conservation of momentum are applicable. Number 4, since the energy of an X-ray is considerably larger than the binding energy of an atomic electron, therefore the electron can be considered as being free. Based on these assumptions, Compton was able to derive a theoretical result exactly agreeing with what he observed in his experiment. Let's go through the calculation how he made this theoretical model successful to explain his experimental data. So let us first derive a relation for the momentum of photon in the context of relativity in Einstein's photon theory. According to the special theory of relativity, the relativistic mass m of an object with rest mass m0 moving with velocity v can be expressed through the equation m equals m0 divided by 1 minus v squared divided by c squared, where c obviously stands for the speed of light. Squaring this equation, we can write m square equals m0 square divided by 1 minus v square over c square. In taking the denominator of the right side to the left side, we can again write it as m0 times 1 minus v square over c square equals m0 squared. Removing the brackets, we can put it obviously into this form, and then multiplying each term with c4, we can write it m squared c4 minus m squared v squared c squared equals m0 squared c4. And each term can individually be put into the form of a square as shown in this one equation, and I denote this equation by 1, where p equals mv is the momentum of the object, E equals mc squared is the relativistic energy, and E0 equals m0 c squared is the rest mass energy of the object. Substituting these values, equation 1 can finally be put into the form pc whole square equals the difference of the squares of the relativistic energy and rest mass energy, that is E square minus E0 square. And I denote this equation with 2. Equation 2 in fact relates the relativistic momentum P with relativistic energy E of an object. For an object with zero rest mass, the rest mass energy E0 goes to 0, And equation 2 can be expressed in the form PC whole square equals E square, removing the square and writing the equation into the form P equals E divided by C. And I denote this equation with A. So equation A in fact gives the momentum of photon in terms of its energy. Now let us merge the Einstein's photon theory with this relativistic equation. According to Einstein's photon theory, the energy of a photon equals h times its frequency. That is, E equals h nu, where h is Planck's constant in nu is frequency of photon. Substituting this value back into equation A, the momentum of photon can be expressed as h nu divided by c, or it is equal to h divided by lambda, where I have written 1 over lambda equals nu divided by c. And lambda obviously stands for the wavelength of the wave. Compton visualized his experiment as shown in the cartoon. Consider a stationary electron of rest mass energy equals E naught equals m naught c squared. A photon of energy E equals h nu is approaching along x-axis, colliding with electron and scatters in the xy plane with an energy equals E prime equals h nu prime. The electron recoils in the opposite ordinate in the same plane. As is visualized in the cartoon, the scattered photon has a longer wavelength. According to law of conservation of energy, the total energy must be equal to the final energy of the system. That is, E sub I equals E sub F. Now, the initial energy consists of the photon energy and the rest mass energy of electron. The final energy contains 3 parts, that is, the scattered photon energy, the rest mass energy of electron, and the kinetic energy of electron. So, applying the law of conservation of energy, the equation can be put into the form h nu plus m naught c square equals h nu prime plus m naught c square plus Ke, where Ke is the kinetic energy of electron. Now I can sum up the rest mass energy and kinetic energy, giving rise to the relativistic energy in the form E sub E stand for relativistic energy equals m naught c square plus Ke. With this substitution, the above equation can be rewritten into the form h nu plus m naught c square equals h nu prime plus E sub E. And I denote this by equation 3. Now, according to equation 2, the relativistic energy of electron in terms of momentum P sub E can be expressed as E sub E equals P sub E times C square plus E naught square, the whole square root. This would be equal to PEC whole square plus M naught C square whole square, the whole square root. Also, V equals C divided by lambda. Substituting these values, equation 3 can be rewritten into the form hc divided by lambda minus hc divided by lambda prime plus m naught c square equals p sub ec whole square plus m naught c square whole square root. Squaring both sides of this equation and making a little arrangement, it can be put into this form, where I have first squared both sides of the equation, removing the square root from the right side, and then taking m naught square, and then taking m naught c square whole square to the left side, and the c square with p multiplied by with p sub e, and the c squared with p sub e is taken to the left side, which multiplies as 1 over c squared with the whole term. And I denote this by equation 4, which gives me the square of the momentum of electron in terms of the wavelength of incident radiation or incident photon. So we can say that equation 4 links the energy of incident and scattered photon to the momentum of scattered electron. Another very useful relation between the momenta of the two particles can be established through the law of conservation of momentum. So let us apply the law of conservation of momentum. Since momentum is a vector quantity, therefore we would treat it through vector algebra. Let us first understand this geometrically. The incident photon and the recoil electron are making angle theta and phi respectively along the direction of incident photon. Therefore, both momenta, that is the momentum of photon and the momentum of electron, must have x and y components as per vector algebra. And we further know that the conservation of momentum holds for each component independently. Therefore, we can write these equations, where in equation 5 I sum up the initial momentum of photon and electron at the left side, where at the right side I sum up the momenta along x-axis of photon and electron, and I am denoting that by a superscript f. Similarly, in equation 6, I sum the initial momenta of photon and electron along y-axis, and at the right side, I sum up the final momenta of the two particles along y-axis. In order to solve this equation, we need first to find the momenta of the two particles along x and y axes, both before and after the collision. As can be seen from the figure, before collision only the photon carries momentum along x-axis as the electron is stationary. So the initial momentum along x-axis is just equal to h divided by lambda for photon and equal to 0 for electron. After collision, the photon moves with a longer wavelength whose momentum is given by p prime equals h divided by lambda prime. This momentum has both x component and y component. By resolving this momentum, the x component just become as pxf equals h divided by lambda prime cos theta, and the y component become h divided by lambda prime sin theta. The component of the momentum of electron along x and y components can be expressed as Pe cos phi and Pe sin phi respectively. Substituting these values into equation 5, we straight away get h divided by lambda equal h divided by lambda prime cos theta plus Pe cos phi. And similarly, substituting these values into equation 6, we can write 0 equals h divided by lambda prime sin theta plus Pe sin theta. And I'm denoting these results by 7 and 8. Now, the change in wavelength of the scattered photon can be obtained by solving equation 4, equation 7 and equation 8. That is solving the law of conservation of, solving the equation obtained from law of conservation of energy and the two equations from the component of law of conservation of momentum. To this end, let us first write equation 7 and 8 into the form h divided by lambda minus h divided by lambda prime cos theta equals P sub e cos theta. And similarly, from equation 8, I can write h divided by lambda prime sin theta equals minus Pe sin phi. I denote these equations by 9 and 10. Now let us square these equations independently. If I square equation 9 first and open up the square at the left side, I can write h divided by lambda whole square plus h divided by lambda prime whole square minus 2h squared divided by lambda prime cos of theta equals p sub e squared cos squared theta. I can write it as h divided by lambda whole square plus h divided by lambda prime whole square minus 2h squared divided by lambda times lambda prime cos of theta equals p sub e square cos square phi. And squaring equation 10, it can straight away be written as h squared divided by lambda prime square sine square theta equals pe square sine square phi. I denote these two results as 11 and 12. And if I add these two equations, and I can write the result as h divided by lambda whole square plus h divided by lambda prime whole square times cos square theta plus sine square theta minus 2h squared divided by lambda prime cos theta equals p sub e whole square times cos square phi plus sine square phi. Now, using the trigonometric relation between the square of cos and square of sine, that is cos square x plus sine square x equal to 1, the second term at the left side would go to 1 and the last term at the right side inside the bracket would go to 1, and the equation would reduce to this simple form, that is h divided by lambda whole square plus h divided by lambda prime whole square minus 2h square divided by lambda prime cos theta equals p sub e squared. And I denote this equation by 14. Now we have derived two equations for the square of the momentum of electron, which is equation 4 and equation 14. So I can compare these two equations with each other, and comparing the two equations, I get this lengthy equation. Now first expanding the square of three terms at the left side and then cancelling similar terms in the equation and arranging the equation, we can express it in the form m naught times c times 1 over lambda minus 1 over lambda prime equals h divided by lambda times lambda prime, the whole multiplied by with 1 minus cos theta. Now taking cross product at the terms at the left, I can write this as m naught times c, the whole multiplied with lambda prime minus lambda divided by lambda prime equals h divided by lambda prime times 1 minus cos theta. Or it can be arranged into the form delta lambda equals h divided by m naught c 1 minus cos theta. Equation 15 is the result of the theoretical setup of Compton model. Let us see how this result can explain the experimentally observed data of Compton experiment. One thing more, delta lambda in this equation is called Compton Shift. Now it is quite obvious from this equation that the Compton Shift is independent from the incident wavelength, time of exposure up to the X-ray source, and nature of the scatter, because none of these quantities appears at the right side of the equation. It depends only on the scattering angle theta of the scattered photons. Now let's see what we get. If we substitute theta equal to 90 degrees, then obviously cos theta equals 0, and we are left with h divided by m naught c. And if we substitute the value of all the three constants, that is h, m, naught, and c, we end up with the number 0.02426 angstrom. This value of change in wavelength is called Compton wavelength, and it is usually denoted by lambda sub c and is written as lambda sub c equals h divided by m naught times c. Now, on the other hand, if theta is 180 degree, what would we have? Cos 180 degree equals minus 1. So the term inside the bracket would become 2, and we would have delta lambda equals 2 times h divided by m naught c. Similarly, for theta equals 0, we have cos theta equal 1, and the term in the bracket goes to 0, so delta lambda equals 0. That means the Compton shift varies from 0 to a maximum value of 2 times h divided by mc. Now, this may be possible for the incident photon to interact with the tightly bound electron within the atom and cannot be detached. In such situation, the whole atom recoils, thereby scattering the photon in all directions. So for such situation, we replace the electron mass m naught by capital M, which represents the total mass of the atom. And this is obviously many times greater than m naught. With this replacement, the Compton shift become immeasurably small, and in such a case, we just get the incident wavelength.